Okay then guys, little intro for Simpsons Rule here. Here's the general formula. It's to approximate the integral between two bounds a and b, two endpoints a and b of y dx. So here's your first start point a, say here, and here's b. And you were approximating the integral, the area under this curve here, between a and b. Basically what you do is you divide the region here into n intervals. So if you've got n intervals, you'll have n plus 1 ordinates for the x-axis. You start at x0, you increase by this distance here. You divide b minus a, the whole length, by the n intervals. And here's your interval distance, which we label h. So you go up by h each time, all the way up. The formula emerges. I'll just mention it here. Here it is in practice. We'll do the derivation in a moment. So basically you do h over 3. H is, as I say, the distance between each of the intervals. So it's the interval distance. So it's h over 3, bracket, the first and the last y ordinates added together, 4 times all the odds in between, and 2 times all the evens in between the endpoints y0 and yn. And that's it. That's how you remember the formula. So now we're going to derive it. What we'll do is we'll build it up bit by bit. Basically, Simpsons rule uses a parabola to approximate the curve. So here's our curve then, and I've done a dashed line for a parabola. And I've said this parabola, which is just a quadratic parabola, a quadratic is a parabola. So you've got this quadratic that runs through these 3 points. You've got 3 equations in 3 unknowns that you can solve for a, b and c. So you can fit a quadratic to these 3 points here. And that can then approximate the area, because you can just take the integration of the quadratic. Here's point x1, say. There's back a distance h, there's forward a distance h. So we're just going to look at this area here and show how the formula emerges. So the distance is h, as we said. We go back h and we go forward h from a point x1. The y0 then, if the parabola meets the top of the curve here, here, and here. For that to happen, you've got 3 equations in 3 unknowns. So the y0 value will equal, basically you put this x value into the input values here and here. So you get that equation. Then you put x1 into here and here in the quadratic. And then of course you put the x1 plus h in both here and here. And you get the value of y2. So you need to solve these 3 equations in 3 unknowns for a, b and c. And we can do that, can't we? Generally speaking. So what have we got now? Well, the area under the parabola that we've just mentioned is simply this integral. Here's the quadratic. As we said, the parabola. Integrate between x minus h, x1 minus h, and x1 plus h. And that integral there. And we can integrate cube over 3, square over 2, isn't it? Powers of x, constant integrates constants times x. Then input x1 plus h in the x values, here, here, and here. Take away the lower value, and then you just put in the x1 minus h's in these input values here, here, and here. So then we claim, and I'm going to show you how we get this actually. So we claim, using that formula, which I'll keep in mind, that the area, this area, just simplifies to h over 3 y0 plus 4y1 plus y2. So I'm going to show you for b and c. And then I'll leave you worry about A, because I've only got a tiny bit of room here to show you. So if we look at this area then, if we look at the C terms, the terms with C in, okay, in all this expression here. Alright, and then I'm going to look at the C terms in this expression. So let's look at the C terms in this one, because it looks a bit easier to work out. So this would be the right hand side, and we're working out the terms with C in. So h over 3. And it's y0, 4y1 plus y2. y0, so there's a c there. 4y2, 4y1 is 4 c's, and then y2 is another c. So in total you've got 6 c's. So the right hand side is just 6ch over 3. Now the left hand side. So let's look over here then. Now we've got c x1 here. And we've got cx1 there. Okay, so what have we got? So we got cx1, but it's minus cx1 there. And we've got ch and minus ch. So we've got 2ch here, haven't we? Because the cx1's cancelled because there's a minus here. So we end up with 2ch. The 6 over 3 just becomes 2ch. So you can see now that this is the same as that. The 2ch's are equal. So again, this line equals this line in terms of the c multiples, doesn't it? Now let's look at the b's to see if they're the one and the same. So let's get rid of this little bit of work here and here, and we'll look at the b terms now. So I'm going to look at the b's that emerge from here, the b multiples. So you're going to have h over 3. So this is the right hand side, and you're going to have h over 3. Now the b terms, you've got this one, bx1 minus h, plus this one, the first and the last. Can you see that the h cancels here and here, and you'll just get 2bx1 and 4 of these, so you're going to end up with 6bx1s. 6bx1s. Now what about the left hand side in terms of multiples of b? Let's have a look here. We've got this term here and this term here. They're minus one another, and they're a simple quadratic. We've got a b over 2 common, so let's just write a b over 2. Then we've got this quadratic, take away this quadratic. Now the x1 squared, take away x1 squared will cancel. We've got 2x1h minus 2x1h, which is 4x1h. And then the last term, the h squared, take away, and you'll just get h squared here, which will cancel because minus times a minus is a plus, and then you take it away with that minus. So there's the middle term that just emerges. So you end up with 4 over 2 is 2, so you've got 2bx1h, and here on the left hand side 2bx1h. Yeah, they're the same. So the a multiples in this expression, the b multiples and the c multiples both equal one another, and it's not difficult to show also that the a multiples are also the same in these two things. So that's why we can go from this line then to this line here. And I'll leave the fact that the a multiples, simply because I haven't got enough room. It is slightly more awkward, but it's not really that difficult to show that the a multiples are also correspond to equaling one another. So that's why we went from that line to that line then. So here is the nub of the solution then. We've got the area of this little grid with 2 intervals on. Now if we go along another pair of intervals, a pair of strips, we can see if we move along to say y2, 3 and 4, we can get the same area here but with regard to y2, 3 and 4. So it'll be the same as this, won't it? But just the next pair of strips along. And when you add these two strips, you'll get h over 3 as common. You'll get y0, 4y1, but the y2's combined to make 2y2's. And then you've got a 4y3 and a y4. So here's the addition of both pairs of strips. So that's for 4 strips or 5 ordinates. So we've got 4 strips. Now if we added on another pair of strips, you can see that you'll get 2 of these, 2 y4s again, 4 y5s, and 1y6, as I've put here. Just add 1 there. The 141 gets added on to this y4, and you get this arrangement here. So you can see now evidently the general pattern of Simpsons rule emerges, because here we've got the first and the last added, 2 times all the evens in between, and 4 times all the odds. And you can continue that same pattern, and just continues in the same way. So that's Simpsons rule then. The only thing I've left as a tiny little exercise, and I know it's awkward, is to do the algebra to show that the a terms for this is equal to the a multiple of this expression here, using these 3 equations. And that's it really. So that's Simpsons rule then, something we can use, and it's best done by examples anyway. So all the best with the examples, guys, and I'll catch you in the next section. Cheers!